It's not doing a countdown anymore. So I don't know when it starts. I don't know when to say, hi, and thanks so much for showing up for Math Learning. It's Mr. Jennings, and we are sketching polynomials today. So another thing that's available to you are the whiteboards. The whiteboards are super cool and useful. They've got space for your rough work and space where you can sketch your polynomials. They're up at the front. You may use them if you like. Go ahead and grab. Our main goal is we want to make connections between polynomials, between their graph and factored form and their equations. So let's take a look. You should be able to, given a factored form equation, sketch the graph. So when we're looking at a sketch, here are the things that we want to have on it. All of our intercepts and end behaviors. Someone asked me if you're going to sketch the local maxima and minima.
Yes, you are.
The local maxima and minima. Ask me, hey, are we also going to do those, Mr. Jennings? They seem like significant points.
Are we going to, Mr. Jennings?
Nope. You're going to do that next semester in calculus. That's a calculus question. Okay. I'm happy to walk people through how to do it, but it's actually kind of like we need to unfold that topic for you, so that's very extra. But if you want to look at extra, we certainly can, but it's not something that we require right now. You could test a few points and get sort of a rough idea, and of course throw things into Desmos, always tells you. So these are the main things that we want to have in there, our x and y intercepts and our end behaviors. Okay? Yeah, let's go. So when you're looking at the factored form of a polynomial function and its graph, like let's say we have a quadratic function here, something we're very familiar with. What does this, and this tell you about this function f of x? Here's our a value. What does that tell us? -2. Our leading coefficient will be -2. What does that tell us?
Negative or positive reflection over the x-axis.
Sure, yeah, so we have a reflection over the x-axis, so connecting to our like transformations from grade 11, I like that. Direction of opening, this parabola opens downwards, right? It goes like this. It could be describing the position of a marker as it flies through space, which I can't catch for some reason. Yeah, so we get direction of opening from that one. Where is its x-intercepts? Where does this one, if I sketch it, cross the x-axis? Yeah, so we set each factor to 0. So if you have x plus 2 equals 0, then we subtract 2 from both sides of the equation to get x equals -2. Good. So we have one of our roots there at -2 and one at +1. This one gives us a positive root. Those are sign flippers. Some people talk about x always lies, and I think that's a mean thing to say about your x's. You're probably responsible for 50% of the problems yourself. So I would just say, like, we want to flip the sign of that one because we set each factor to 0, rather than having a weird story about our x's. So how would you find the y-intercept of this function? I know that it opens downwards, so it's doing something like this. Yeah, there's a big parabola there. But how will we find the y-intercept? Mr. Jennings says we need to provide all the intercepts. Yes, excellent. We're just going to expand and simplify that thing to standard form. Is that what you were going to suggest? Yeah, and we can even just expand and simplify the part that gives us the constant term. We just want the constant term. The constant term gives us our y-intercept. So in this case, I can tidy up my scratches around there, and I can just take -2 times 2 times -1. That gives me +4. This is the point 0, 4. And I can check that. Another way that I can do this is just input 0 into the function and evaluate. So if I just input 0, you'll see I'm doing the same thing. Expanding and simplifying to standard form will give you the whole thing in an expanded form, but it's a bit of work. or just evaluate the constant term. Cool. So you might check your work in Desmos and find that this is absolutely true, -2, 0, and this is 1, 0. Good. So y-intercept is input x is 0 into both of these spots and evaluate. So when we're looking at quadratic functions and polynomials of higher degree, we can just extend those ideas. Oh, another thing we didn't talk about over here was end behavior. A quadratic is an even polynomial, and it has this end behavior. They go off to the same direction, and because we're negative leading coefficient, it goes down. That would be the same thing if it was to the 4 or to the 6. Okay, so over here, what degree is this f of x, the first one?
3.
Yeah, good. So this is a cubic function. It's degree 3. What's our leading coefficient going to be if we expanded that to standard form? There's going to be an x cubed term, and there's going to be a number multiplying x cubed. There's just one. Yeah, it's just we will multiply this times this times this. That gives us our x cubed. It's 1. So our end behavior is as x goes to infinity, y goes to infinity, and as x goes to negative infinity, oops, that was weird. My brain did a weird thing, as it's known to do. As x goes to negative infinity, y also goes to negative infinity. Okay. And the x-intercepts. So this one gives us -1, 2, and -3. So x equals -3, -1, and 2. And the y-intercept, anyone know it yet?
-6.
-6 is good. Yeah. So we can just find all that stuff. I think the easiest way to find the y-intercept is to literally set x equal to 0, because that works not only for polynomial functions, but for any function. You want to find its y-intercept, x is 0 there, so set x equal to 0, and then find it. Okay, now over here, what degree are we here? We are quartic, because we have an x to the 2, and then another x, and then another x. Each one we accumulate our factors. That's good. So, sign of leading coefficient. Yeah, we are negative here. This one was positive, +1. This one, our leading coefficient is going to be -2. Okay. And then, so we are negative. That's good. And our end behaviors, we have, it would be described as Q3 to Q4 behavior. We are doing this dance, just like a parabola that opens downwards, because we are an even degree polynomial, so we open downwards. Practice by looking at these in Desmos, getting to know how they're opening and the way in which they're going off to infinity in both directions, if you want to review. Our x-intercepts, what are they? Yeah, so x equals 4 and -2. And then what about this one? And that's 1. And one of these roots is not like the others. So the 1 is a bounce root. This one will touch the axis and then turn around right at the point where it's a root, because it's squared. So let's actually just pop in and take a look at that in Desmos for fun. We have, this is like, your habit. You're going to be like, oh, I'm going to take a look at some of these and get to know them. -2x -1 squared, x plus 2x minus 4. So we just type it in. -2 multiplied by x minus 1, and the bracket, square the bracket, and then x plus 2, and then the other one was x minus 4? X minus 4, there. So it looks like this. So here are your roots, -2 and 4, and then right in between them is this bounce root at 1. We see that the function goes up very, very high. We don't quite have the skills yet to locate those local maxima. And in fact, these are absolute maximums. We can notice that because this one is symmetrical, it has this absolute maximum at 40.5. If it wasn't symmetrical, one of them would be higher than the other. We're worried about that in calculus. We're not worried about this yet. But we definitely want to know the end behavior. And the end behavior, as it goes off to infinity, down in both directions. It goes down so sharply that really to look at that, I really need to like increase my scale of y. So if I increase this to like, minus 1,000 or maybe 10,000 there, 100,000, 1 million, and you can see there's our characteristic quartic shape. And the little wibbles that we could see when we were zoomed in, they've disappeared, and all we have is that general quartic shape that's happening there. And that's by changing the scale, I can see that end behavior a little more clearly. Okay, play around in Desmos. Okay, and how would we find the y-intercept here, besides look at it in Desmos? Yeah, you said -2 times -1 times 2 times 4? It's a little trickier here because we have this squared factor. I believe the easiest way, the most accurate way to find our y-intercept is just to set x equal to 0 and evaluate. So when we evaluate f at 0, we have -2 times 0 minus 1 squared times 0 plus 2 times 0 minus 4. Okay, so -1 squared is 1. So that's 1. So -2 times 2 is -4. -4 times -4 is 16. Y equals 16 when x equals 0. We've got a Desmos ready to go. So let's check that out. Let's undo our changes to the scale. That's good. And we zoom in at 16 and find that it is true. There's our intercept. Hooray! We are correct. Good. Okay. And this one here, we have another quartic. We have a drag root there at what value? When do we have a root there? Our degree is 4. Our leading coefficient is positive. We are positive 1. And what's the root that we have there? What's the -1/2? Good. So we have x equals -1/2 because we just set this factor to 0. So -1/2 will do it. And then we have x is 3, this root. This one is a drag root. So we're imagining that it's going to just touch the axis and skid across it before going down. And then our y-intercept is, find our y-intercept. Someone tell me the y-intercept for this last one. -3. Yeah, very straightforward. Set this one to 0, and you have 0 plus 1. That's 1. 1 cubed is 1. 1 times -3 is -3. Y equals -3. Good. So, and then our end behaviors, we are doing this dance. We are up and up. This is the more formal way of recording it. So this is what you will do when asked for that on a test. This is, your understanding. We're just visualizing. Nathan? No, you're just, yeah, okay, yeah, good. So we need to show all these things on our sketch. The x-intercepts, the y-intercept, and the end behavior. We don't need to show exactly these local maximum and minimums. That's calculus. Okay. All right, so let's sketch some. All right, here. First, I notice that I am cubic. And I notice that I have a positive sign, so I'm going to be some shape like this, with this end behavior and that end behavior. Okay? So x plus 1 gives me a root at -1 there. X minus 2, so that gives me a root at 2. And then a root at 3, at -3 there. So I have one there. And then I look at that and I'm not satisfied. I'm not satisfied because I feel that I can stretch that out. Maybe I make each point 3. So here is -1. Here is -2, -3. And then here is plus 2, so that's 1, 2. And I'm just going to space this out a little bit. That's like x is 1, this is x is -1. And then let's find our y-intercept. So I set x equal to 0. So f at 0 is equal to 1 times -2 times plus 3. That's -6. So I'm down there at, here I go 1, 2, 3, 4, 5, 6. Notice that my scale on the x-axis and y-axis are not the same, and that's fine. So I want to have this end behavior clearly shown. I'm going to be coming up, coming down again here, going through this y-intercept, turning around and coming up. And then, to make it more beautiful, I label them as minus 1, 0, minus 3, 0, 0, minus 6, and 2, 0. There. That's a fine sketch for all the marks. I didn't bullseye my points. I'm filled with regret for not bullseyeing my points with my sketch. I'll do better in the future, but I'm still going to give you full marks for that. Okay? I've noticed some people, particularly in grade 11 with trigonometric functions, will like sketch. Like, you know, like the way you would sketch your partner's nose, and they'll do this and they'll sketch it. Yeah, that's not what we mean by sketch. Okay, just it means like a sketchy picture. All right, let's go. This one here, are we quadratic, cubic, quartic, quintic? We are quartic. What's our end behavior? Do the dance. Someone get kinesthetic. Yeah, that's it. We do this dance. Okay, and then so we've got our leading coefficient. Our roots are here at x is 1, minus 4. So here I'm going to space every 2 steps is 1, because I can get my plus 4 in there. So I have 1, 2, 3, 4, 5, 6, 7, 8. That's 4. Okay, and then I have 1, 2. That's 1. And then I have there, this is my negative root, so that's 1, 2, 3, 4, that's 2. Okay, so I just do my roots that way so I can space them out a little nicer and use the space a little more beautifully. And then I want to find my y-intercept. So how do I do that? I believe it to be 16. Does anyone want to debate my findings? Is it? Let's find out. We have f at 0 is going to be equal to minus 2 multiplied by 0 minus 1 squared times 0 plus 2 times 0 minus 4. So this is the same thing as saying minus 2 times 1 times 2 times minus 4. Ha ha! How dare anyone ever doubt me? That's 16. I'll make lots of mistakes, but this isn't one of them. Okay. So, put 16 on there. 1, 2, 3, 4, 5, 6, 7, 8. There. Every one is 2. And then that's nice. So I've got I stretched it out by 2 that way, and I compressed it by 2 that way, whatever, you know. And then I remember my end behavior is down in both directions, and one of these roots is not like the others. Which root is not like the others? 1. It's a bounce root. So I have my end behavior here where I'm coming up. I go through here. I come down. I mistakenly gave the impression that that's a local maxima or minima. It's not necessarily that. And then let's go down this way. And I indicate my end behavior here. I indicated my end behavior there, but not here. This should have an arrow on it as well. Okay? So I can probably improve this a little bit by, I think it's probably going to be something like this. Without doing calculus, I think it probably has a maximum over there. Comes down, bounces, and comes down like that. That's kind of what I would imagine. And then if I want, I can label some points, right? Actually, not if I want. I really ought to label some points. Yeah?
How do you estimate where like the maxima is?
I could do like a kind of like averaging, like that bounce root is really going to have a bigger impact. Things are going to be pulled towards it and stuff. Okay. Yeah. My answer is don't worry about it. But a really good way of estimating it is to look at it in Desmos. That's a joke. That just gives you the value. And then over here, this is 4, 0. Okay. This is sketching. Okay, this is our skill for today. You good with that skill? Can I get going? Yeah. Be well. Okay. Hopefully see you tomorrow. Okay, this one here, f of x. We are quartic again. Okay, I see 3 roots there at minus a half. and then 1 root there at 3. So I got to get 3 on there, so let's do every 2 as 1. So there's 1, 2, 3. There's one of my roots. And then over here is 1/2, but negative, so that's right there. Halfway to -1. That's my drag root. I am positive leading coefficient, so I do the dance. All right. And then, yeah, we go to the same club. All right, and then what? Oh, I was thinking about something. We need to find our y-intercept. So Weston, what's our y-intercept here? Good. So I'm going to put that at -6, but I'm just changing the scale. 1, 2, 3, 4, 5, 6. Let's put it there. That looks good. So we are drag root here. So we are doing something like this. We're coming down. We skid across here and then come down. It probably goes way, 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 way down there and then comes up. And that's a cut root, so it's moving real fast. I didn't bullseye it again, and I feel such shame. But, you know, you're just gonna have to accept me as I am. -1/2, 0. And this is 0 minus 3. And this is 3, 0. There, beautiful sketches. Let's keep going. So, you already did this. That's great. You're doing that in your groups. And then here is your, you know, these were the sketches for the ones if you sketch them on your handouts. This is what they look like when Metherall sketches them. She doesn't even label her intercepts. It's a good thing you're doing it with me, right? Not with Metherall. Who wants to do this course with Metherall? Yeah, she's fantastic. Y'all be lucky to be in her class. So, finish the polynomial graph match. There's an extra worksheet for you to complete, and then the textbook on page 39 has some practice problems. Go!